Southeast. And a more academic talk for you folks this morning. A little bit about software complexity, programmer understandability. It's not the compiler that has trouble understanding our software, it's us. A little discussion about software maintainability. Can we reduce the complexity by tools, or can we reduce it by techniques? A finite state machine, I think most of us have had in some form of a computability course, or maybe in some type of an EE course or a wiring course. And it's going to be a small program with a single input does a simple thing. And it might be a long thing, you know, producing a long sequence of characters, reading a file, producing a set of character records of some form. So it's not always necessarily short running in time or short running in the volume it deals with, but just we want it to be short or small in complexity. Deterministic. Now, a finite state machine can be coded like most of our vending machines used to be, and you can now actually, I've always been able to, you really want to be able to code it to where it fits on one page. A nice pick of the finite state machine. Deterministic finite automaton is a subset of the FSMs. It has 4 tuple, has a set of states, sets of transitions, a start state, a set of accept states. These can be either more machines or merely machines, those from the EE type world, whether the inputs or the actions happen on the transition between states or actually within the state. And it doesn't really matter to me from a software point of view which of those is being used. For example, if you get a standard compilation or compiling technology, you can have a finite state machine. And in this case, we have an SFM that's going to be accepting a star B plus, which would be any number of A's, including 0. So we start symbol on the left-hand side, the funny looking arrow, and we stay in the A state as long as we see a lowercase a on our input stream. If we see a single B, then we, whoop, I'm missing an arrow on my B state there, sorry, but still working with it. If we see a B, that actually ends our input, and then a non-accepting state are the thin line states, and then a thick line or double circle would be an accepting state. So this would be the first layer of a compiler type program, but it's also, it does some computability, it does something reasonable, and actually you can draw a picture of it. So it becomes a way to where if you can get the picture from the code, it becomes part of a proving technique, and I'll use double quotes on that, to where you can show that to people who are not necessarily coders and say, okay, this is what this particular piece of code does. So the whole idea is to try and find our code, deal with the complexity, and break it up into pieces that are not complex. DFA, they have higher reliability. There is discussion in the mathematical academic world. Is it a proof or is it a show? You're showing that your input works in a certain way, or your programs work in a certain way, but it's not necessarily quote unquote a mathematical proof that those from 9th grade algebra and geometry that we've all been through. Mathematics is often a modeling method used to try and find ways to represent things that happen in the real world. But proofs themselves are social constructs. And the mathematicians, when they prove a new, they call it a new result, and they have developed a new theory in mathematics, someone writes it up, they think about it, and then they distribute it, and other people have to kind of vote on it. Other mathematicians look at it and see if it's proper or improper. So there's lots of social, at some point we accept and say, okay, that is accepted mathematics and that's approved. But early in the proof's derivation, it is actually still being reviewed by other people. And that brings up an area called diagrammatics, which is, I'm not sure if it's a real area at this point, but it is, mathematicians tend to work in the way they have worked showing proofs. paper and pencil and lines that were written predicates. And can we accept a proof by a diagram? If you see, going back a slide or two, if we see a finite state machine like this, and programmers, given the inputs to this type of a program, if we have a program written in a common language, can we establish a predicate at the end of this and say, okay, at the end of this execution, that a truth exists, a file has been read into a data structure of some form. Because so diagrammatics is how much can we extend the concept of proof to include pictures. Okay, so I've been working on a tool, and this would be a example of the finite state machine we had before, in that we have transitions, and that's the bottom half of that particular piece of code. I don't know how well you see it at that distance, but this tool reads in a series of, it's a language, reads into a syntax, and it describes a finite state machine. So it's going to have a name, what type. The FSMs I've been working with so far are dealing with characters, dealing with records. So having an input stream of records can be processed. Having an input stream of lines, so an entire line up to a carriage return line feed. It lists, we have a start state, and at the start state, we are going to execute, in this case, a routine called hello. We have a series of acceptance states, and then the language be an output, and then if there's any inclusion file that needs to be, and that's referencing common.java. And then the transitions. So these transitions are going to be the transitions between the different states. And when you accept this, or you code it, and so my coding happens in this kind of an environment, little editor, and typing this text. And then when I run it, it actually outputs a Java program which implements that picture from previous slides. So in this case, the bottom right-hand side there is the common. That's the small. Those are the common.java. Those are the small routines that I reference in that tool. So running this tool actually produces a Java program that is equivalent to that finite state machine from the earlier slide. Now there's another tool that's available out there, open source, called GraphViz. Inside of it, it has a program called Dot, and some of you might have used it. It actually has a way, and what it will do is if you send it a text file, it will try and draw the equivalent DFA from it, or finite state machine. So from my code, the library I'm using actually produces this text file automatically. So backing up 2 slides, I just code that upper piece of code. That's the code I type in, or a coder would type in. And then this text file is produced automatically from it. And if you send it to Dot, it automatically produces a picture. So we have a small computing component that will produce a diagram that, for folks of a certain flavor, EE type folks, vending machine builders or whatever, that look at that and think, oh, I know exactly what that machine is going to do. So now you're dealing in terms of pictures instead of just terms of, oh, thousands of lines of programs and hundreds of routines and layers and layers and layers of data structures. I'm sorry, layers of data abstraction in the data structures, which is just more complexity. And that is a copy of the Java code that was produced. So I edited that little, 12-line file, and then a finite state machine was generated from that in Java. So this is the Java file that actually is compiled and executes in representation of what we had in the picture. And this one's hard to see, but this is actually that particular piece of program running, accepting any number of A's and one B. So it's a small little component, didn't do a whole lot. But what I'm trying to do in the bigger picture is, I kind of glossed over before, is I'm trying to find ways to where can we get these small components and can we organize them in such a way that your data is not being buried inside of large unwieldy programs. Because every time that we extend the more memory available in a computer somewhere, somehow, some computer you buy, oh, it's got more memory, 2 gigs, 8 gigs, whatever. Programs that inhabit that computer just get bigger. That's what the programmers do. They can save more. And that makes all the other problems, some of which we're seeing and hearing about, static analysis of code, problems just get bigger because the code gets bigger. So we need, I think, we need to be finding ways to reduce the complexity. So can we take and organize our finite state machines in a way to where you are one component has one input, produces an output. Then another component will take that as an input. You can do this on a command line pipe. You know, look at the DOS prompt, C:, I don't have a copy of it here. I think I got a picture. Let's way later. Hold on, where is it? It's like the last. There we go. There's an example. Line 4 there, where you're typing the output of a file and then typing in the input. So we got pipe going from one component to another component. Can we, if we get our data out of our programs up into the operating system, now you have a sequence of records that can be sent to a database, or you can write recognizers to test it, to verify it. You can say, okay, coming out of this component is a series of characters that are character records, line it occurred on, code, the character name, character number, whatever, what column it was in. So you can put descriptor records around to your data and then put it as an output pipe. But that can either be input to a database to another object, another finite state machine, or can we take the data and check it for verification purposes. So the idea is to make our data more shallow, not in depth in our programs. Because inside of programs, how many places can you hide data? All right, one thing I figured out as an educator is you can hide data very deep in a program. You've got global variables, which software engineers tend to dislike from a security point of view. And then you have data structures, which can or might or might not be correct with our pointer operations and aliasing and other things going on. And then procedures where you're renaming stuff. So there's lots of complexity on our data structures and our data inside of programs. So we want to try and eliminate that by making our components smaller, doing less, getting data out of the program into a data pipe or into a stream to where it can be tested, verified, and then dealt with inserting in databases. Now, let me back a couple of slides. Okay, we covered that one. The fox, screen, and chicken problem, I think most of us have seen. It's a purely academic, and sometimes it's the monkey and some other animals, something. And the thing is, I was really surprised. I taught an artificial intelligence class recently. Thank you. And this showed up, and I've actually, it was in a paper of mine I wrote about this problem, but it showed up in an AI class as a tough search problem. And I thought, no, yes, it is a tough search. It's a search problem for an AI, but it's also, it's a finite state machine in that you can represent it as, it doesn't take 3 arrays and 4 while loops and a third data structure to represent this. It really is an FSM. When you start moving things across the river and make sure it's safe, that the grain's not eaten by the chicken and the chicken's not eaten by the fox or whatever. And I don't necessarily want to go explain the full finite state machine, but and you do have some loops, as you can see, because you can go back on a lot of those, or almost every state you can go back. So what actually the problem, going back, what was it? Fox chicken grain problem is really a grammar. You basically are establishing legal strings in the life or a problem of fox grain and chicken. Is this string that you have, the man moves first? No, that'll work, won't work because man has to take something across to leave the system in a safe state as he goes. But it's an FSM. So many of our problems are analyzable at this level, but we don't do it. We throw it into the AI class and say, well, that's AI. No, it's not. It's simpler than that. So if we had an input string, and that's on the bottom there, CE, let's see, what was it? Man moves the chicken first. Each character is a movement. And the second one, E, is the man comes back empty across the river. Then he takes the fox. Then he brings the chicken back. Then he takes the grain over. Then he comes back empty. Then he takes the chicken over, and now he's in a safe state. So the problem of man, chicken, fox, grain is a language problem. It's just they throw it into a search problem and say it's AI. So we need to analyze our issues more. So I've been playing with hooking the FSMs, finite state machines, into a flow to where you have standard out, every process having 3 standard files, but hooking standard out in a pipe into the standard in of the next one. And in this case, we're doing some scanning and tokenizing. As an academic, you always pick the easy problem. So if you're going to do piping, you do the compiler, because it's all layers. You got 4 or 5 layers to go through. And you can describe, and the thing is, in a problem like a compiler, if you can pull parts of it out and say, okay, the first part's a finite state machine, the second part's a finite state machine, and we can both draw pictures with those, then it's hard to have a bug in there. I'm not saying impossible. I'm saying it's harder to have a bug in those 2 finite state machines. And now you get to the bigger part of your problem, where you're going to be doing a parsing and language acceptor and all the other things that you do in a high-level compiler, optimizations, then finally output. And those are probably not going to be finite state machines. Those are going to be more complex pieces of code. But instead of having a 5,000 line program, which we were trying to dig through and see if we could verify, you were able to take 20 lines off, 50 lines off, in one finite state machine, 50 lines off another finite state machine, take off 20 lines at the other end of the sequence of process, and get that as a finite state machine. And now all of a sudden, your complex code that you have to really concentrate on, instead of being the full 5,000 lines, is half of it. So the whole idea is to isolate the simple parts away from the really complex part. And then to have, not necessarily insertion points, but points where your data is so shallow and available to be tested that it's easier to test it, as opposed to having someone give you a big program and you find you have data structures inside of data structures and trying to figure out where you can test things. And I was really surprised at the discussion yesterday on static analysis and how little success it is under certain problems. So we want our programs to be smaller and less complex. So get the simple stuff out. Finite state machines expressed in programs are complete programs. They can lead to parallelism, because if you have processes piping P0, pipes to P1, pipes to P2, pipes to P3, you have multiple CPUs that's automatically, you're piping from one to the other, automatically they're parallel. Not restricted to a single language. If you decide you want to use a language for a specific, one of the layers or one of the FSMs, you can do that. You do not have to have all the same language in your sequence of SFMs. Those components are not sharing spaces, not sharing namespaces, not sharing variable spaces. All the data is output to the standard out. So you have less security issues. There's no security problems between P0 and P1, two processes, two finite state machines, because they don't share anything except the data pipe that they're producing. This limits the programming options, and that's good. One of the, I don't know if it's surprises, but as a long-term educator, one thing you find out is the C students still graduate. And sometimes, when you're giving students, oh, you've got the problem here and you've got a language and you can do all kinds of things in this language. You've got all kinds of data structures you can build. You have all this extra complexity. And then if the code works, and they pass their test cases, okay, but was that the minimal set? Was that the most maintainable code for long term? So we want to reduce the complexity as much as we can to the appropriate level of complexity. So I think that our lead programmers, it'd be reasonable for lead programmers to be restricting things to say, okay, this program shouldn't need more than one array, or this program shouldn't need more than one this or one that. Instead of just saying, okay, whatever problem you're trying to solve, you have the full flavor of the language you use, which means you can do all kinds of complex things in there. So I recommend data being in a single layer in the surface pipe, in a pipe between finite state machines, and try and eliminate the complexity of data at deep levels within our software. And that was an example of, I had 3 or 4 finite state machines in a sequence doing things, and I was saving stuff off in the text files so that you could test or look at it and see intermittently, so I didn't have to tear a program apart because the program was already torn apart because I built it in pieces. So in conclusion, software is complex, and the newer languages actually make it worse. I love the scripting languages and stuff, but if you screw up your own data structure, here's a URI, go out and whack something off the web from inside the language. So it's the more choices we give inside of our languages, that doesn't make the problem easier. Once again, the programmers need to be understanding their code, and if it's broken up in parts, and some of it, most of it, a lot of it is broken up in pictures, then it's easier to examine what goes on within your system because it's taped up on the wall. And in 70% of it's in finite state machines, and the other 30%, okay, that's our problem area. Most of cost of software is maintainability. I'm not sure about NASA numbers, but in the real world, 80% of software cost is maintaining the software after it's built, after the person understood it, finished it, walked off, did something else. Then someone else comes along and says, now what do I do? We can reduce this complexity with tools and with techniques. It doesn't necessarily have to have new languages. Sometimes it's just, all right, you can do FSMs by just breaking up bigger problems in the languages you're already using. Although I am toying with the language tool. Oh, and there we go. 5 minutes. Thank you. Any questions?
I'm just wondering, I could typically take the software in our project and run it through your tool, and it would identify the finite state machines that are within. I don't know, is it that practical?
Not yet. That's the area I'm going to. Okay, my research started years ago, and I was doing program understanding, writing a program to understand other programs. And now, and every time I've got something working, it's, oh, I could take it back another layer, and then take it back another step and fix another problem. And that's what I'm working on now, which is, can we take a tool that can look at a piece of software and say, okay, this area might be an FSM, this area might be an FSM. In general, it's the control statements. If you've got a for loop, that can probably be taken to an FSM. That just depends on what you do inside of it. If it's nice and simple, or are you doing something complex? So yeah, I'm still analyzing software, and I'd like to be able to find FSMs that existing. I really would. That I don't know if that's computable.
Okay.
Are there any questions on the phone?
One moment, please.
Have you looked at applying it to testing and designing graphical user interfaces? But there's a lot of interesting applications, state machines in that area. That might be something that could be looked at.
No, I have not stuck. My interest area has been program understanding and compilers. That's the area I've really stuck with. I haven't. I've seen GUIs. I look at GUIs, but I haven't tried to figure out how to approach it. Okay. Thank you.
We do have a question from the phone, however, I was not able to hear their name. So if you did just press *1, you may go ahead and speak now.
Go ahead and speak.
Hey, hi, this is Bob Winstow. I enjoyed the presentation, and I see how this is good advice for a developer, but I'm wondering how we would use this in IV&V. Give us any tips toward that.
Frankly, I think the IV&V folks need to be shoving it at the developer, saying, "We want this." It's not most languages, when they've got everything in them plus the kitchen sink, that professionals, you put everything into one big program, and you don't break it up, because going to a database, quote unquote, is just too slow to do, or something like that. And I think the IV&V portion is important enough. We want the data shallow, and we want it out of that program, and you want it someplace else, probably in some form of a pipe or database, to where it can be. We want to be able to start establishing predicates that you finish layer one of your program, and now you could make a statement that the first finite state machine's done. As opposed to when you look at a 5,000 line program and it's just running, it's like it's hard to prove or show or understand what's going on anywhere in there. So we want to break things up, make them shallow. I think for testability purposes, it is very important to do this kind of stuff, but it might have to come from the testers to say this is the kind of stuff we're expecting to start seeing. But it also might be on people like me to go back to some of the common programs to see if we can pull the FSMs out of those. One of the things I've been playing with is looking at some of the Unix utilities and seeing if I can pull a couple of SFMs out of it to where that, a common utility, I don't know, listing, LS. So you've got a couple of it, portions of the program would be FSMs and a portion would not be. So try and reduce the complexity of that program. So, it's a push-pull way or problem, but I think it's important.
Hey, I agree with you that it's important. I've used these in development that I've done in the past before I was working IV&V. One idea that I had, and maybe you can tell me if I'm completely off base, would be perhaps we could use these FSMs to find the different outputs of a piece of code by simplifying it into an FSM and then verifying that against the way the developer chose to implement it. Because honestly, in my experience, telling a developer how to develop code after he's already gotten started on it, you may as well just start banging your head on the desk now. So I just wondered if you had any input on that kind of use for your FSM approach.
Well, I guess it would have to be, if there's some kind of testing standard that a program has to be developed against, that these things shall be showable at the steps when they're finished. You know, so a lead programmer would have to be able to look at the program and say, okay, at the 4 or 5 things we're going to do, this program is going to do, that we want these things to happen at certain times in a certain timing sequence. But still, a coder can take that and conglomerate it together in one big program. So, and therefore, and you've got the data shoved deep inside of procedures, inside of data structures, inside of procedures, locals, you still don't have the shallowness that I think you need. Yeah, there we go. I got a solution. There's a problem, or this is a possible solution, you know, to a somewhat a good-sized problem, but I don't know how. It's not, I guess, well-defined enough or mature enough to where we could say, okay, you know, this is the tool you've got to use on your project. Well, we're not there yet, and I'm not sure if we can get there. I think we can. So.
We're ready for our break now. If you want to continue this discussion, we can go over to the breakout room. But we will start back right at 10 o'clock. So 15-minute break. Thank you, everybody.